Hey ANPers, this is Dr. Jones checking in. This is ANP2 lecture test 3 video, I think 12. And again, I am trying to make the videos a little shorter so that they load to YouTube faster. And I'm assuming that the shorter videos are also easier for you to digest. But so don't let it terrify you that we have more videos for each test so far. Okay, so I have a big, actually kind of a little pink post-it in the middle of page 20. And right below, it's like covering words. And right below that, it says 24 cardiac output equals heart rate times stroke volume. So I'm guessing that's where we left off. So, next slide. Cardiac output equals heart rate times stroke volume. Yeah, that's on the test. There's not a lot of numbers on these tests, but the formulas absolutely are. And I do need you to understand the concepts behind the formulas. If cardiac output is heart rate times stroke volume, that means that you're multiplying. So what happens to the cardiac output if you increase the heart rate? Well, you're multiplying. So let's give this an example. Yeah, I'm okay with red. So if your heart rate, just to give random numbers, is 2 times 3, stroke volume is 3, so 2 times 3 is 6. So if you increased heart rate to 4, what does that do to your cardiac output? Well, it increases it. What if you decreased it to 1? Well, then you'd decrease it. What happens if you increase your stroke volume? Then you increase your cardiac output. What happens if you decrease your stroke volume? Then you decrease your cardiac output. So these are what we call directly proportional. When you increase the heart rate, you increase the cardiac output. Increase the stroke volume, you increase the cardiac output. Decrease the heart rate, decreases the cardiac output. Decreasing the stroke volume decreases the cardiac output. Okay, so these relationships are very important and you are responsible for them. The math, not so much. I do have, if you're taking this test online, I do have the Respondus set to allow a calculator in the top, along the top of the screen. So on the off chance you would need it, I've never seen anyone need a calculator during a test before, but you never go wrong with a calculator. Okay, oh, yes. My coffee mug, I did put cinnamon in it today, a little more than usual, and I do like it better. Oh, and Pepper the pupper is in the room, but she is asleep in her little doggy bed, so as long as the kids don't make enough noise to wake her up, we should be good without doggy distractions. Fingers crossed. Okay, so what is cardiac output then? It is the amount of blood pumped by the left ventricle in 1 minute. And again, the amount in the left ventricle and the right ventricle are equivalent, but we're going with the left ventricle because it feeds the systemic circuit, and that's the one we're generally most concerned with in a medical setting. The equation for calculating cardiac output, I've said about 10 times now, and you should have memorized. And, okay, so let's talk about, let's actually math for a second. Let me whiteboard us. Oh, W, hey. Okay, so let's talk about cardiac output equals heart rate times stroke volume. Okay, so heart rate is measured in beats per minute. So that can be written as BPM, beats per minute. But the per really means divide, beats divided by minutes. So we can write that as beats over minutes, because a fraction is really just a division problem. In fact, that's like the division sign is just a fraction with a generic numerator and denominator. Here's your math joke for the day. We don't get for a lot of math jokes, but today we're getting one. There's a fine line between a numerator and a denominator, but only a fraction of people will get this joke. My kids think that one's hilarious. Okay, so the numerator is the top number, denominator is the bottom number, so beats divided by minutes is our heart rate. We're going to multiply that by the stroke volume, and the stroke volume is the amount of blood pumped with each beat, and the amount here is going to be measured in milliliters per beat. So if you've already had algebra, you know what's coming next. If you've not had algebra yet, this stuff you're going to need to know. Okay. So the beats cancel out. How is that possible? Okay, what is anything times 1? 5 bundles. There's 5 masks in a bundle, and you get 1 bundle. How many masks do you have? You have 5 masks. There are 25 masks in a bundle, and you get 1 bundle. How many masks do you have? You have 25. So anything times 1 is itself. Here's the other kicker. Here's our pie. I'm going to make quarters. So if the numerator is going to be, you're going to eat 4 quarters of this pie. The numerator is how many of these quarters, and the denominator is how many divisions there are. So like, it was supposed to be round, sorry. That's 1 quarter. Okay, so if you eat 1 of these, you've eaten 1 quarter of the pie. If you eat all of these, you've eaten 4 quarters of the pie. And how many pies is that? That is 1 pie. Now, if you took the same pie and cut it into 10 divisions and then ate all 10 of them, how much pie did you eat? 1 pie. Now, the discussion about what kind of pie would you eat is a separate but also interesting discussion. My daughter told me the other day, which I had known but hadn't realized, that she's never ever tried rhubarb. She's like, what's rhubarb? I was like, well, it's what you put in strawberry pie because it's too tart to eat by itself. So strawberry rhubarb pie. It's good stuff. It's even better than strawberry pie. And then she said, I've never had strawberry pie. And I was just completely gobsmacked because my grandma used to make the best strawberry pie with like strawberry jello with strawberries in it with like her own homemade like pie crust. And it was like, it was the stuff of my childhood. It was strawberry pie with the occasional strawberry rhubarb pie thrown in when the rhubarb was in season. So now I gotta make strawberry pie. I'm terrible at pie. So if you eat 10/10 of the pie, you've eaten the whole pie. If you eat 4/4 of the pie, you've eaten the whole pie. If you eat 1,000,000 millionths of a pie, if you cut it into teensy weensy little bitty slices, you've still eaten 1 pie. All of that to say anything divided by itself is 1. And 1 times anything is itself. Okay, so these can be, because we're multiplying, these can be rearranged to milliliters per minute times beat divided by beat. So what's the one thing we know about anything divided by itself? That it equals 1. And we're multiplying here by 1. And what's anything times 1? Itself. So it's not necessary. So we can just cancel out these beats divided by beats, and we're left with milliliters per minute. So that's why the cardiac output is reported in milliliters per minute when you start out with beats per minute times milliliter per beat. Milliliters per minute, cardiac output. Okay, so continuing, given the average heart rate of 75 beats per minute and the stroke volume of 80, I apologize, my handwriting with the mouse is not getting better. I still blame the mouse. Milliliters per beat. Okay, so we know that we can just cross the beats out. They cancel out, they don't count. So then my calculator a few years ago said that 75 times 80 was 6,000. So that gives us 6,000 milliliters per minute, which milliliters, 6,000 milliliters. So let's just simplify that. So that's 6 liters per minute. And another note, just again, you probably already knew this. Liters per minute, and that's the same thing as liters per minute. All the same thing. Liters per minute, liters per minute, liters per minute. Whether you put one on top, do the slash, or write out the division as the word per. It's all the same. All right, so our average cardiac output is 6 liters a minute. Okay, going back. That one do it? Yay. Okay, so our heart rate is, of course, how many beats per minute, how fast is your heart beating. Stroke volume is, of course, the amount of blood that you move with each heartbeat. Okay, next, how do we calculate stroke volume? It's end diastolic volume minus end systolic volume. So it's the difference, and when I say the difference between EDV and ESV, I mean the math version of difference, which is literal subtraction. Literal subtraction. Okay. The end diastolic volume is, of course, the amount of blood in the left ventricle at the end of ventricular diastole. The ESV, the end systolic volume, is the amount of blood left over in the left ventricle at the end of ventricular systole. So in our toothpaste example, the EDV is how much toothpaste you started with. The stroke volume is how much toothpaste you squeeze out onto your toothbrush. And the ESV is how much toothpaste is left in the tube when you put the cap back on and put it back in a nice, neat, and organized fashion. Everyone in your life will thank you. Okay, and then there's a neat picture of how this is related to bicycle pumps, the physics of bicycle pumps, the one-way valves, and how it pulls the blood in and then squishes the blood out the other way, and it works because of these one-way valves that the pressure cannot push backwards. And there's the other little one-way valve. So that's why. Physics is the basis of all of science. And math is the basis of all physics. So, like, biology is based on the chemistry, which is based on the physics, which is based on the math. Does that make the biology most important because it's the top of the list? Or does that make the math the most important because it's the basis for everything? You want to get into a science argument, that's a good one to get into. Not with me. Clearly, anatomy is most important to us right now because that's what we're talking about. That's what the test is going to be on. So I am on page 21 now. That didn't work. Page 21. Top of the page. Factors innervating the heart rate. Please read through those. Actually, we'll come back and talk about this. The autonomic, actually, let's talk about them individually right now. Autonomic innervation. Heart has a dual innervation by both sympathetic and parasympathetic. And that's what dual innervation means, is that it has both sympathetic and parasympathetic innervation. Both ANS divisions innervate the cardiac plexus. The cardiac centers in the medulla oblongata control the heart. I'm certain I have a slide for this. Yeah, there we go. And these are the cardiac centers. That's a bracket. It doesn't look like a bracket. It looks like a eagle. It looks like a malformed seagull. Sympathetic control of the heart. So what is sympathetic going to do to your heart rate? It's going to increase your heart rate and also increase the force of the heartbeat. So which of these is going to control sympathetic? The cardio-inhibitory center or the cardio-acceleratory center? Right, the cardio-acceleratory center, because sympathetic increases the heart rate, and this has acceleration right in the name. So this one is sympathetic. And the parasympathetic control of the heart is in the cardio-inhibitory center, which slows heart rate. OBS. Oh, and then here's cardiac plexus. Okay. Cardiac reflexes. An increase of cardiac activity can be caused by a decrease in blood pressure, a decrease in oxygen, and an increase in carbon dioxide. The resting autonomic tone is that you get both sympathetic and parasympathetic innervation to the heart at all times, all day long. In a healthy resting heart, the parasympathetic dominates. So you're getting both sympathetic and parasympathetic, but the cardio-inhibitory center is stronger and sending out a stronger signal. Oh. I heard a car door. Hubby just got home, and I wondered where my father-in-law went, and he just got out of the car. And so that's where he was with him. Okay. And a healthy, where he said that, you can decrease the heart rate by increasing the cardio-inhibitory center, increasing parasympathetic, and you can decrease heart rate two ways. You can decrease the parasympathetic, or you can increase the sympathetic, or both. 3 ways. So you can increase heart rate by decreasing parasympathetic or increasing sympathetic. Pacemaker cells. There we go. So how exactly does sympathetic and parasympathetic increase and decrease the heart rate? It changes the ionic permeabilities of the cells in the conducting system. Just write it down. Parasympathetic neurons release. Okay, so here's our resting, where we're constantly drifting up to threshold. So this is our normal at 75 BPM. So in parasympathetic, we're constant releasing acetylcholine, which of course is ACH, and it opens chemically gated potassium ion channels. So which way does potassium go when you open a potassium ion channel? Sodium, like fools, rush in, potassium rushes out. So what does that do to the inside of the cell, which is normally negative? Well, it's normally negative and you're losing positive ions, so it's going to hyperpolarize. It's going to make it go even. So here's the distance from threshold normally. It makes it physically further from threshold. Farther, further. A longer distance away from threshold. So potassium rushes out, makes, and so since it's further away and it's depolarizing at the same rate, it always depolarizes. It's not that it's slower, it's that it's further away and it takes longer. It's going at the same rate as it always does. It's just further away. And that therefore slows your heart rate because it takes so much longer to reach threshold again. Sympathetic releases NE, northeast, or Nebraska, or norepinephrine. Norepinephrine for us, for now. And that opens sodium ion channels. Sodium, like fools, rush in. And relatively negative on the inside, relatively positive on the outside. Positive rushes in, that makes it depolarize, which brings it closer to threshold. So without that, it takes this long, and we're just physically closer to threshold. And so it's not that it moves at a faster pace, it's that it moves at the same pace and it has less distance to move. It's just starting closer to the finish line. So it doesn't take as long. So sodium rushes in, making it take less time to reach threshold, thereby speeding the heart rate. It's just closer together. Next page. Okay, we're going to finish chapter 20 on this video because I'm ready to be done with this chapter. Venous return is the amount of blood that returns to the heart from the veins. Venous return. The Bain bridge, reflex is an atrial reflex. When you increase the venous return, it increases heart rate. And there are stretch receptors in the right atrium, and this does increase the sympathetic. Hormones that increase heart rate are epinephrine, norepinephrine, and T3, which makes sense. What factors affect stroke volume? EDV and ESV. Okay, now, this isn't as simple a relationship as the multiplication was for the cardiac output equals heart rate times stroke volume, because this is a subtraction. So this difference can change. So if we increase EDV, what does that do to our stroke volume? It increases it. If we decrease EDV, what does that do to our stroke volume? It decreases it. So that is proportional. What if we increase our end systolic volume to here? What does this do to our stroke volume? It decreases it. So these are inversely proportional. When you increase the ESV, that decreases the SV. When you increase the end systolic volume, that decreases the stroke volume, because it's just physically moving it further up. What if we decreased the stroke volume? What would that do? Or decrease the end systolic volume, what would that do to our stroke volume? It would increase it. So when whatever we do to the ESV, it does the opposite to the stroke volume, because you're subtracting. So if you subtract a bigger number, there's less left. If you squeeze more toothpaste out, there's less left. If you squeeze less toothpaste out, there's more less in the tube. So, and then I've got room for you to draw these. Let's see, here's what it looks like on mine. I've got volume in milliliters, and then go 1, 2, up to EDV, stroke volume, ESV, and then it increases with time, and those are milliseconds. So, What was EDV again? In diastolic volume, which is the volume in the left ventricle at the end of ventricular diastole. It's how full the ventricle gets. Filling time is the duration of ventricular diastole. It's how much time the ventricles have to fill. So the faster the heart rate, the shorter the filling time. So as we mentioned before in the videos, increasing the heart rate can decrease the filling time, which can actually decrease the amount of oxygenation to the tissues at extremes. Preload. Next slide. Preload is directly proportional to EDV. It's the degree of stretching during the ventricular diastole. So it's the load preload. Stretching. The greater the end diastolic volume, the larger the stroke volume, as we said. More in, more out is called the Frank-Starling principle, and this is an LE principle. It's a concept. The PAL principle is the principal of your school, who is your PAL. But this is a concept principle, so it's an LE, not an AL. Doesn't work for everything, but so the more in, more out, the more blood that goes into the heart, the more blood it pumps out. In systolic volume is how empty the ventricle gets. Page 23, last page of chapter 20. Yay! Contractility is the amount of force produced during a contraction. Positively inotropic are things that increase the force of the heart contraction. Things that are negatively inotropic decrease the force of heart contraction. And some inotropic factors include ANS, hormones, and some ion concentrations. ANS on contractility. Sympathetic stimulation has a positive inotropic effect. Increasing contractility, it releases epinephrine and norepinephrine, that's E and NE in the parentheses. The net effect is that it, I was going to point to it, increases the force of contraction, increases the stroke volume, and decreases the ESV, which is end systolic volume. Next bullet, parasympathetic, has a negative inotropic effect and which decreases contractility. It releases acetylcholine. Of course, the parasympathetic system is entirely cholinergic. It only has acetylcholine, which is ACH, and that produces hyperpolarization and inhibition, which don't remotely fit on those blanks. Sorry. As a result, you decrease the force of contraction, decrease stroke volume, and increase ESV, so the opposite of everything sympathetic did. That's where I'm pointing at. Hormones with positive inotropic effects include epinephrine, norepinephrine, glucagon, and the thyroid hormones. I haven't talked about glucagon for a few videos. The afterload is the amount of tension required to open the semilunar valves. And the afterload is increased by vasoconstriction and decreased by vasodilation. Okay, so a list of factors that affect cardiac output. I'm going to just read my bullets. I'm not going to find them on the picture. Excuse me. More coffee. Nectar of the gods. First bullet. Sympathetic increases heart rate, parasympathetic decreases heart rate. Again, I'm sure it's on this picture somewhere. Epinephrine, norepinephrine, and T3 increase heart rate. Third bullet, increase venous return, increases heart rate. Fourth bullet, stroke volume equals EDV minus ESV. Next to last bullet, have I taught you the word for that yet? I don't remember saying that on a video yet. Okay, so the last thing, the last bullet is the ultimate. And the next to last is the penultimate, P-E-N-U-L-T-I-M-A-T-E, penultimate. Okay, so the penultimate bullet, the next to last bullet, is EDV, filling time and venous return, filling time, venous return, and ESV, which is changed by preload, contractility, and afterload. Preload, contractility, and afterload. Aha, found it. And the cardiac reserve is the difference between resting and maximum cardiac output. And this has been chapter 20. Yay, we're done. So this has been A&P 2, lecture test 3, video, oop, I moved it, I set it down, 12. And we started in the middle of page 20 and finished page 23 all in one video, and I don't have my phone and I don't have a timer on, so I have no idea how long this took. Apologize if this got long. So thank you as always for tuning in. The education must go on. Dr. J out. After I find my keyboard. Control, Command, Escape. Have a good one, y'all.